So hello everyone, welcome to our fourth video. So in which this video we are going to talk about the different type of support conditions in FEA, and what we will do is that we are going to go through the mechanical GUI and see that what are the different support conditions that are actually exposed. On top of that, we will also try to understand what these support conditions are actually doing in the background and how they are working. So just to give you a background about the support. Support in finite element analysis is a computational way to mimic the way the component is held in the reality. So usually any FEM tool offers different way in which we can replicate the reality. One way is to directly apply the constraint over the degree of freedom of the discretized element. So this is actually going to be the focus of this video. To start, as we know that any FEA software tool start with a CAD geometry, and after that it is going to discretize into elements. Exceptions are IGA methods, meshless methods. Once we discretize the CAD is discretized into set of elements. Each element is made up of set of nodes. These nodes have associated degree of freedom to it. Now the support condition allows us to us to apply the constraint directly at these nodes. So suppose this is your elements and this is composed of a multiple set of nodes. So you can see the numbering. So this is numbering has been shown for a single solid elements. So it will allow you to directly apply the constraint over these nodes. Now usually most of the FEA tool offers different elements to simulate any computational model, but the common elements that are actually used are solid element, cell element, beam element, plane elements. So these are the commonly used elements. At this point, it is worth highlighting that all of these elements doesn't have a same nature of degree of freedom. So just to give you an example, if we talk about a cell element single node, so that node is going to have a 6 degree of freedom, 3 rotation, 3 translation. But once we talk about any continuum level elements like your plane element, which is used to model plane stress, plane strain, axisymmetric type of simulation, or solid elements that are actually a volumetric elements, they don't have any rotational degree of freedom associated for each node. Now just to show you like whatever I was talking that solid elements doesn't have any rotational degree of freedom, let's test this over a very simple model like whatever we were discussing. So this is some simple cantilever type of beam. So here it's a volumetric representation of your CAD. At this point, if I'm going to mesh this model, I know the 3D elements are going to get generated. So as this is something that is a very coarser mesh, so I'm going to run a model analysis. So that will not going to affect much unless until we are concerned about the accuracy. So let's go with this mesh only. Now at this point, suppose what I do is that I use a fixed support. So I will next explain what this fixed support is actually doing. So for a time being, as we learn in our mechanic of material courses that whenever we are going to apply any fixed support, that part is not going to translate in any direction and also not going to rotate. So suppose if I apply a fixed constraint over this edge and run a modal analysis. So if all the rigid body motion are constrained properly, it means that there are no zero modes that are going to get reported in a modal analysis. So let's see what happens. Now if I'm going to look at this thing, so I can see that one zero frequency value is getting reported. It means that even though we had applied one fixed support, still some type of rigid motion is getting generated inside the model. So let's see what mode shape results are there for that. Let's animate this. So if you look at this image or this animation, I can clearly see that this body is trying to rotate about this edge. So what actually happened? So again, now if we go to the elements, so this is a solid element. Now solid element only have a translational degree of freedom. It doesn't have any rotation degree of freedom. So even though when we are applying a fixed support, it is only constraining the translational degree of freedom. It is not constraining any rotational degree of freedom. Now as all the nodes are collinear, that's the reason the rotation is not something that is constrained for this model. So I hope this part is clear. But suppose if you convert this thing this body as a cell element. So let me show you that also. So now let's open the same model in the workbench. So once we open the model in the workbench, we can use this mid surface option to convert any solid body uh, as a cell element. So whenever we usually this approach is applicable only for thin structures. So that is something that we will discuss in some upcoming tutorials. But for a time being, keep in mind that you can use the mid surface tool to convert any solid bodies as a cell body. So here you can see this body I have converted as a cell body, and the body will look something like this. So this is something like a surface element. Now, if I'm going to open this body inside the mechanical, so that is going to look something like this. Now, let me first go here. So you can see the thickness value is something that is coming from the space claim. So this thickness is nothing but whatever the values that got extracted from your solid body. So let me assign the material properties, that is a structural steel. Now, next is that suppose at this point I want to visualize that how it is actually looking with the thickness properties. So I can go here, thick and cell beam, and if I'm going to mesh it, now this will show me the cell with the associated thickness property. But keep in mind this is just for the visualization purpose. Let me switch it off. Now, as we were discussing that for when we applied the fixed support for along one edge for a solid element, still there was one rotation or the rotation, rigid body motion, or the rotation about that edge. Now let's do the same thing for this cell body. For cell body, if I'm going to use the fixed support and run the analysis, we can see there is no rigid body modes. It means that this body is no more rotating about this edge. So why it happened? So the reason actually lies in the concept that we were discussing, that each element nature is not something same. So solid elements have translational degree of freedom for each node. Cell element have translational plus rotational degree of freedom for each node. So when we applied a fixed constraint for this cell element, it means all the translation and the rotation degree of freedom are constrained along this edge. So that's the reason this body is no more free to rotate about this edge. Okay, so now we will take an example and we will go through in the details of all this support conditions that are available in mechanical. And finally, I will also share some of very good materials that are available in context of the Ansys Mechanical for determining like which support to use in Ansys Mechanical, and there is a dedicated course, a structural boundary condition for stress analysis, and there is one very good video type of support in structural analysis. So I will not go into like whatever has been already covered in this video, but I will try to show you what actually happens in the background of this fixed support and what it is doing for that whenever you are trying to apply it over any model. So once we open any model inside the mechanical GUI, we will see number of support conditions. At this point, usually users get multiple questions in mind. If you are not getting any, that's also fine. I hope that by end of this video, you will start getting some of the questions that might come into your mind, and we might have already discussed the answers for those questions. So let me give you a few examples that questions commonly comes whenever a user starts the mechanical GUI. Like why there are many support conditions, what these support conditions will do, what ANSYS is doing in background to apply these support conditions. Can we activate, deactivate these boundary conditions? Can inclined radial tangential support be applied? So let's take a deep breath and start the discussion. So if we look around, any structure or machine, a part of the machine, usually they are either attached to the ground or there is some relative motion between two components. So if we recall our mechanics of material basic course, so you will we can recall like usually we discuss different type of support conditions like roller support, pinned support, fixed support, simple support, and each support is actually serving a different purpose. Now, if we again go back here, so again, you will see there Ansys provides a different way, but fundamentally, Ansys is also trying to provide a way using which user can reproduce the physical situation under the computational environment. Now, the next question is that if we talk from finite element method or finite element analysis perspective, so these support conditions apply some type of constraint on the selected node. So as discussed previously, even though you select a surface, body, edge, you are still selecting a set of node. Only thing is that robust preprocessors like Ansys Mechanical makes our life easy in selecting those nodes. Now, if we talk about what actually happens in the background, because if we look from the GUI point of view, we are applying some fixed support. But we can think what is actually happening from the finite element perspective, or how this GUI selection is getting converted at the solver level. So for that, each boundary condition is actually represented using APDL commands. If you are not much familiar with the apdl command, no need to worry. Ansys actually writes out a file that is called as a dsdat file, in which it shows the logic that is used to implement the support conditions. Remember, help manual is always your first best friend whenever you are trying to understand anything in detail. So always keep the Ansys help manual handy. So while trying to understand any of those boundary conditions or any of the feature that is available in the GUI, that is going to be very helpful. Even though in some cases, if you want to further extend those things, there are ways like using the command snippet, we can use the features that are not even accessible through the GUI. So enough talking on this thing, theoretical part. Let's go to the GUI and demonstrate how Ansys actually implements this boundary condition in the background. So let me open the model that I think the dummy model that we are using to run the model analysis. So if just to give you an overview, so first, we imported the CAD geometry. So this CAD geometry can be either imported from your any CAD tool, or you, if the geometry is simple, you can directly create those geometries inside the space clip or design modeler. Now then we define the material properties, and the stiffness behavior is flexible. It means that we are letting this body to deform. Other options are like rigid beam, beta. So these options are also available, but they are something that is used for different applications. Once you start getting familiarized with different modeling practices, then yeah, when you are working with multiple component level assemblies, then you might start using this rigid feature. Now the next is that meshing. So once the CAD geometry, material assignment, and other things are done, then we mesh those things. So by here we are actually using the default settings, but there are multiple settings that are available under this meshing that allows us to uh, control the mesh locally or the globally for any of the component that is present in the GUI, or that has been imported at the geometry level. Now next is that in this case we are trying to run a model analysis, and model analysis will give us eigenfrequency and the eigenshapes. So this was just for the demonstration purpose, but what I will do is that I will select this face. So now as I'm selecting this face, so what I'm telling the solver is that let's constrain all the translational degree of freedom for any node that is present for this selected face. So if we look at this face, and if I activate you the show mesh, so we can see that this is mid side node. So there are a set of nodes that are present for the selected face. Now let me run this one. So at this point, suppose we decide to check what is actually getting implemented in the background. So if you go right click on solution, open solver directory files, So in the solver directory file, you will see there is a file named dsdat file. So this contains all the modeling setup details. So if I open it in a notepad, let me just show you. So I will not go into much detail. Means all the details that is present in the this one. I will directly go to the fix support. So you can see this is something that this part of the dsdat file is used to implement the fixed support for that selected node. So here you can see first it is whatever the phase that we selected, it is creating a set of nodes, or it is creating an extra component for all the set of nodes that was present for this data specific phase. And then it is selecting that phase. CMSEL is actually used to select those means elements or nodes, and then d all comma all. So it is used to constrain the degree of freedom that is present for all the nodes. So I will show you this command also, like detail of the command how you can access. So suppose if you have, so I'm actually using the local help manual. So if you have access to web, so from there also you can access this. Similarly, the commands. So if I go to the mechanical commands, so there is a section called command reference. So under the command reference, if I go to the D command, so you can see the details of the D command defines degree of freedom constraint at nodes. So whatever the nodes that we have selected, so this command can be directly used to define degree of freedom constraint at those nodes. So here, first just to revise, so we selected one phase, but internally solver is trying to find what this all the nodes that are present for this phases, and then it is using a D command to constrain all the degree of freedom. Now under the D command, you will see there are other details also, like if even if you are using multi-physics type of applications, because when we use multi-physics type of applications like thermal, so in that case, your degree of freedom is not going to be the displacement. It will become temperature. So when you use a D command, the temperature is going to be get constrained at that specific location. Similarly, electric, magnetic, acoustic. So you can go through all the details. So it's quite elaborative. A help manual of the Ansys is quite elaborative, and it's written in a very detailed manner. So all the details you will find under the help manual. Now we discussed about the fixed constraint. So let me open one another static structural system, and here what I will do is that the next one is the displacement. So if I go to the displacement tab, so first if you directly right click and just take your mouse over this displacement tab, so it will give you a brief summary of what this boundary condition is going to do. Like here you can see it is saying insert a displacement boundary condition to displace relative to the original location a flat or curved edge vertex by any more component or the of a displacement vector. It means that whenever we are selecting this boundary condition, we are not directly fixing those values to 0. We still have some option to apply some magnitude. Like just to give you an example, let me fix this face on this side. And what I want to do is that I want to move this face by 1 mm in this z direction. So in that case, I can use the displacement boundary condition. And by default, you will see the defined by components is available. Even normal 2 is also available. So in this case, I know the normal is something that is aligned in the z direction. So I can directly give a value of 1 mm. Let me just see one more thing. So this is 6.34. So just for the visualization purpose, let me use 6.34 mm. And for meshing, I will use a setting of 3 because I want at least 2 elements across the thickness direction. Okay. Now if I'm going to solve it, and then let me select this edge, insert deformation, directional, and as I was applying in the z direction, so let me see how it is applying the displacement. Now you can see at this side it is applying a minus 6.34. So whatever the displacement that I had provided. Now one thing that might come into your mind, why this minus sign? So this is because if you look at your global coordinate system, your coordinates positive z axis is aligned in this direction. So anything that is actually going in the negative of this coordinate system will be something that will get a value reported as a negative at this location. Now again, if we check this thing, like what is happening in the background, support, let me just, this was used to apply the fixed support, and now you can see the same D command is actually used, but here instead of putting a value of 0, it is applying a magnitude that we had provided at that location. If we want to fully constrain, we can change this magnitude to 0. So you can see this is something again. Suppose if user wants to apply some type of magnitude instead of putting a 0 value, so there is no restriction from the means, FEA modeling side. You can still use as your user defined values. Now the next is that, let me suppress this one. Next is your remote displacement. So what remote displacement actually does is that it will allow you to also apply rotational constraint over a solid mesh. Like as we discussed, for a solid mesh, the degree of freedom or the every node has only translational degree of freedom. But suppose I want to rotate this beam about x-axis. So what I can do is that I can directly go select this face, and about rotation about x, suppose if I give value of 10, and what I will want to do is that I want to rotate this body about this point. So for that I can go here, create a coordinate system, and then select this coordinate system at this location. Now let me change these values. Now you can see this is going to get applied about this location. So let me run and show you. So here you can see it's actually bending about this point. Now, if I the next thing is that for some complex applications like remote displacement, if we want to see how which element is actually used in the background, because fixed support and displacement are directly getting applied over the node. But whenever we are trying to apply any type of rotational constraint over a solid mesh, it means that even though element is not there, it in the element doesn't have capability to apply a rotational degree of freedom, but we are trying to apply some type of approach which will allow us to apply the rotational degree of freedom. So for those cases, what you can do is that you can go to the solution worksheet, material and element type information. So it will give you a detail of all the elements that were actually used in order to implement this boundary condition. Now here you can see this is using target 170 and conta 174 in the background to create this remote displacement. Same thing, you can go here, open solver directory files, dstat, yes, and here you can see construct remote displacement. So it is creating some type of pilot node. So pilot node will be your target element, and it is putting some type of extra contact element over the selected surface. Now let me see one more thing that will be helpful for this type of applications. Let me go material and element, target, and I will use a plot items. So if you right click plot items and then go to the geometry, you will see the target node is getting created here and your contact element is getting created at this location. So for visualization, you will also see this. Now at this point, I want to ask why this target location is getting shifted to this location. We are applying all the boundary condition at this phase, but we see that target 170 element that is getting created is something that is present here. So the reason is that if I go to this location, So the location of the target element is actually controlled through these sections. So that's why, if you recall, I created one extra coordinate system and used that coordinate system as for controlling the location of the target node. So that's the reason the target element is getting created at this location. That is actually origin of this coordinate system. Okay. So now the next one is your frictional support. So frictional support is a type of support which allows you to restrict the movement in the normal direction of the selected entity. So here, if you see, suppose what I want to do is that, let me just has this one. Okay. Let me suppress this fixed support. So what I will do is that I will use frictional support. Why it is not working? Oh, I think I was selecting the wrong one. So I'm using frictional support to apply some type of symmetry to this model. Insert. You can have a look at I will share one link in which it has been discussed, like how this frictional support condition works, can be correlated with the symmetry condition. Because one thing is that your frictional support, wherever you are applying, it will restrict the movement in the normal direction. Like whatever the nodes are there, that node cannot move further in the normal direction to that selected face. Let me this and run this model. Well, you can see the body is still getting stretched and we are not getting any rigid body motion error. Now, if you look at this one, solver directory file, dstat, you can see for all the selected nodes, it is constraining the, like for this CMSCL. So that is, let me check which friction support Y, D all UX is equal to 0. Yeah, this is frictional support X. So here you can see it is constraining the movement in the X direction. So that is going to be your this phase. So this frictional support was constraining the movement in the X direction. So X is actually normal to this phase. So that was the reason it was putting a D command in that specific direction. So next is your compression only support. So compression only support is something that applies only a compression constraint normal to one or more phases. So it will not work in a tension. It will only work in a compression. So I will this. Let me do one thing. Let me, just for demonstration purpose, I will select this face. I will apply a compressions only support on this face, and let me delete this one. Displacement, I will put it as component wise so that I will have better control, and X and Z I will put as a 0, and Y I will put as a 6. And what I'm trying to do is that in one case I'm trying to press this body, another case I'm trying to pull this body, so that during the pulling I don't expect any resistance to come, and the body can simply lift off in that while pulling that in the plus y direction. So let me just compression only support stiffness, so that is fine. Normal stiffness program controlled. Displacement I will use 2 mm. Okay, 0 2. So let me see, because we have to bring it back again to 0. So 0. Let me run this model. Duplicate without result. Select the full body so that we will see the motion. Okay, it's in Z axis. Okay. But to get a better feel of this one, I will put 10, 5, 10. So now, if we look at the displacement, one another change that I did is that now I moved it in a -2 the distance, so that because at that point only 0 was something that was getting at that point it was getting activated. Now I'm forcing it to move by -2 in the y direction. So now if we look at the force reaction, we will see that as soon as the body goes into compression zone below 0 point, it starts the forces starts building up. It means that compression only support starts providing the resistance to the movement. Now the last one is your cylindrical support and elastic support. So as we discussed the approach using which you can actually decipher the support boundary condition, not even support boundary condition, you can even look at in details of any of the boundary condition that is getting uh, applied in the mechanical GUI. So I hope this will help you. On top of that, because I don't want it to go through the things that has been already covered using some very good videos. Like I will put the link of these videos, how to determine which support to use in Ansys Mechanical, structural boundary condition for stress analysis using Ansys Mechanical. So this is part of Ansys innovation course, and I highly recommend that you, as in case if you are starting up, please go through all the videos of the Ansys innovation course. They are really great videos. On top of that, there is a very good video on YouTube also, type of support in structural analysis. So I will put links of all these videos. You can go through those videos. I hope that will help you in understanding the boundary conditions, specifically for support condition, in a much detailed fashion. So thank you. And in case if you like the video, please don't forget to like and subscribe the channel. Thanks.